Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our new series on equations that changed web handling forever. Why can traction be lost at higher speeds on some webs, but not others? It has to do with the hair's thickness amount of air entrained between the web and a roller that serves as a lubricant of sorts. We also briefly mention on how to manage air entrainment. Stay tuned if you want to increase your line speed without losing control. No worries, kiddos. I'm going to make this as painless as possible. So, how fast is fast? Well, one of my airplanes, this experimental that I designed and built and displayed at air shows, can go about 2,500 meters per minute. That, by the way, is a very ordinary speed for a paper mill winder. However, if you want to even go 1/10 of that fast with your web machine, you will need to know about some serious air handling techniques. The issue you may have is the loss of traction, which means risking loss of both tension and path control. In short, you're likely to go off the rollers and crash, much like hydroplaning on a wet road. However, not everyone needs to be concerned. No worries if you have a rough web, like nonwovens or tissue. No worries if your web is narrow, because the air can leak out the sides. And finally, no worries if you're slow, say less than 30 feet per minute or 10 meters per minute. Everyone else should be worried, or at least informed. The loss of traction is complicated, but roughly looks like this graph of traction versus speed. At low speeds, you have nearly all of the traction expected by the static coefficient of friction. By the time you hit a few hundred feet per minute, your web is likely to be floating or fully floating on air. So, how big is this air layer that is pumped into the gap between the roller and the web? It is only around the thickness of a human hair for common converting cases. Thus, the treatment needs to only be similarly sized. One remedy can come from the web itself. If it is rough enough, say like nonwovens, textiles, or tissue, those surfaces have way more than enough roughness to absorb or park the air. If not, you could microgroove the rollers, which has a geometry much like a phonograph record. However, as many of you would think, this could be an impractical surface to maintain in many cases, even if it functions for the purpose of air handling. Thus, we use larger but fewer grooves to get the same volume of a parking space for the air. One truly impressive field-tested geometry has grooves approximately 1 millimeter wide, 2 millimeters deep, and on a 1 centimeter pitch. That will take you to the highest speed seen in the industry and is quite efficient to cut. Note, beware of widely spaced grooves because most of the surface is smooth and unable to park air. One field treatment is to use masking tape, applied in any neat pattern you wish. The crepe of the tape has more than enough volume to park the incoming air. So, what factors are important? The answer comes from the 40-year-old Knx-Sweeney equation above. The bigger the roller radius, the more the air is brought in. Not surprisingly, air entrainment gets worse at higher speeds. Finally, air entrainment is reduced with web tension. Note, that a similar looking equation applies to wound rolls that are wound without a nip. Since most wound rolls are bigger than most rollers, air entrainment during a simple center winding can be notable, especially as its effect on loosening the roll and on certain defects such as the air buckle. A side note is that this equation applies to fluids, and that includes liquids. Since the kinematic viscosity of a liquid is several orders of magnitude higher than air, you can expect full floating, perhaps before you even reach 1 meter or 1 foot per minute. Much is known about this topic. The easiest treatment by far is Module 3 of my award-winning and trademark Web 101 class that has been taken by 5,000 people. A fuller treatment, very nicely done by my co-author Tim Walker, is in Chapter 4 of the Web Handling Handbook. Finally, we have the free Air Lubrication Calculator by AbbottApp. In addition to calculating the height of the air layer, it also suggests grooving geometries. I hope you have been inspired by the elegant simplicity of the traction calculation. Stay tuned for next week's show when we will talk about laminate or curl. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.